So, we're going to begin our discussion on energy and enzymes. Enzymes. It looks like enzymes. Oh, that's weird. Okay. So first of all, what is energy? Energy is not a tangible thing. It's quality. It's kind of like an emotion, like happiness, as we discussed. Energy is an intangible sort of system or a way of keeping track of things. It's essentially an accounting system. In fact, it's very similar to the way we do accounting with money, right? If we think about money, if you go to Walmart, you have money in your pocket. So that money represents a number, the amount of money. Say it's $100. When you go to Walmart and you buy something, you give some of that money. Some of that money goes to Walmart, right? Or whatever store you're shopping at. And so what happens is your number goes down. So maybe Walmart gets $20 and you end up with now only $80. And the number has gone down. The number has changed. Someone has gained and someone has lost. And we call this a transaction. A transaction. Whenever money changes hands, right? And the changing hands of money, there's still $100 here, but it's just in different places. And this is, of course, how our economy works. And we keep track of it by just assigning numbers to this concept called wealth. And then we add and subtract all the numbers and make sure everybody, gets what they deserve, so to speak. Well, the same thing is true in a chemical reaction. And in fact, in any kind of interaction, the universe is essentially transactions. If there were no transactions, nothing would change. Right? Nothing would change. If you imagine us all sitting in this room and not moving, someone walks in and then they leave. And then they walk in 10 minutes later and we haven't moved and we haven't done anything and nothing has changed. They would come in again. Well, they wouldn't see any difference. And they would say nothing has changed. Right? In fact, if nothing has changed, then it becomes impossible to tell how much time passes. Think about that. The concept of time is directly tied to our ability to notice changes and how rapidly they occur. Right? Because in order to measure time, you have to have a change or you have to have an event that you can observe. So even time itself is somehow tied into this energy change. So energy changes are everything that happens. Falling in love is an energy change. Lifting a little baby out of a crib is an energy change. Drinking something is an energy change. Moving your arm, moving your hands, leaves on a tree, turning colors. Everything that happens in the universe is an energy transaction. So when we have an energy transaction, we simply mean that energy is being transferred, the transfer of energy from one thing to another. And just like money, we can keep track of it by assigning numbers to it. The numbers we assign are measured in something called the joule. Joule, right? Now, how much is a joule? Well, those of you who will remember some physics from grade 11, if you took physics, energy is measured as a force times a distance, right? And so if you take a force of 1 Newton and you multiply it by 1 meter, you will get 1 joule. How much is a Newton? A Newton is about the amount of force required to hold up an apple. Not that much. If you think about holding an apple in your hand as gravity tries to pull it down, that's a force of about 1 Newton. So 1 joule would be taking an apple and lifting it 1 meter up. We can do that easily. That's not a lot of energy, right? It's a very small amount. So typically, we see energy measured in the thousands or kilojoules. We use the prefix or kJ, small k, capital J. So we use this word joule to measure energy. Just like we use dollar to measure wealth. And what is a dollar? Well, we kind of know how much a dollar is. It doesn't buy much anymore. When I was a kid, though, I could go to the candy store and get a whole bag for less than $1. Now, most people would walk over a loonie on the ground because it's not worth picking up, right? So $1's changed. But it's a number, and it has a value that we can use. All right, I can't extend my page for some reason, so I have to pause and figure out what's wrong with my smart. Okay, we're fixed. We're back. All right. When we're talking about biology and chemistry, what we're talking about is the energy in and between atoms and molecules. And there's really, I'm going to say, two important kinds of energy that we want to think about that matter to atoms and molecules. Well, there's more than two. It's not, I mean, all forms of energy matter, but when we think of a molecule, like H2O, for instance, there's first of all bond energy. And bond energy is related to the relative position of electrons. Where the electrons are hanging out. Because, as we said before, way back in grade 9, if you have a nucleus, then the energy of an electron is related to its distance from that nucleus. And the further out you go, the higher your electron energy becomes. Remember that. The energy shelves, as they go higher, they are more energetic. And that's because there's an electric attraction that's trying to pull the electron this way. So in order for us to push it away and sort of repel that, we need extra energy, right? We need to sort of go against that to keep that electron very far from the nucleus. It's just like on the Earth. If I want to lift something, the higher I lift it, the more energy I need, because just like this, gravity is pulling things down. And we need to use energy to balance that out. So the position of electrons is incredibly important. And so if we look at the molecule that we have here, they're sharing electrons, and there has been a change. When oxygen atoms are alone, their electrons are in a certain position, and the same with hydrogen. But if they get together and they share, the energy of those electrons changes. Question. Later, we're going to discuss things like photosynthesis, and we're going to talk about energized electrons. What that means is it means the electrons have been pushed further away from their atoms for some reason. You can do that by adding energy. You can add, one of the things we add is heat. So besides bond energy, molecules often always have a heat energy. Heat is a form of energy. And with heat, what we see that as the vibrational sort of shaking of this molecule. As it shakes all around, it vibrates and shakes. And the more heat you add, the more the atoms vibrate and shake. And of course, if you're thinking about these bonds, adding heat and vibrating and shaking could shake them enough to break the bonds. So there's bond energy and there's heat energy. There's also some energy involved in the electric potentials, as we'll see later. The ions that have electric potentials can be moved around according to voltage gradients and things like that. But for now, I just want to focus on these two forms of energy. The shaking heat of electrons and atoms and molecules, and of course the relative position of those electrons. Now, bond energies can be measured. Just like we can use dollars to measure things and find out how much something costs, we can also measure bond energies. So for instance, it's found that a hydrogen-hydrogen bond has an average bond energy of 436. And I'm just going to put up here kilojoules per mole. Remember, we always measure by the mole because it's very hard to find one hydrogen atom to measure. So we measure everything in moles. And so we get these numbers. The carbon-hydrogen bond is 411. And that's because the electrons are in a slightly different position. Carbon is more electronegative. It pulls the electrons tighter to itself. So in this situation, those electrons are closer to the carbon atom. And if they're closer, that means they're in a state of less energy. So you can see how it's all related. OH, the OH bond 459. And if I just continue my chart over on this side, maybe I can squeeze one more in here. The nitrogen-hydrogen bond, 391, not as much. Then we have the carbon-carbon bond, which is only 346 kilojoules per mole. The carbon single bond oxygen is 359. The carbon double bond oxygen is much greater. It's 799, a very high energy bond. And then the oxygen-oxygen double bond is also fairly high, 494, but not nearly as high as the others, or as this one. Oh, let me see here. Okay, so bond energies. We're not going to be memorizing any of these numbers. We just want to have a relative sort of idea as to which bonds are stronger, which ones are, I shouldn't say stronger, what I should say is which bonds have more energy, which have less energy. The key thing, though, of course, is that if we want a chemical reaction to happen, let's put for a chemical reaction to happen, the first thing that has to happen is that bonds have to be broken. And that, of course, requires some initial energy. So we have to figure out, first of all, where this energy comes from, and we have to talk about ways that we can change the amounts of energy that are needed. We sometimes call this the activation energy. The activation energy, which is the energy that's required to sort of get something to happen. And of course, that's because we have to break apart some bonds. Now, of course, this activation energy can come from anywhere in order to make this happen. And typically, things like heat can provide activation energy and cause reactions to happen. We know that reactions will happen far more rapidly in a warmer environment than in a colder environment because heat is present. But with biological systems, we can't just rely on random temperatures and random heat influxes to cause reactions to happen. So we need a better way to regulate and control it. Right? Heat causes things to shake, and when things shake, the kinetic energy of shaking is added to the system, which means it can then be exchanged for bond energy, right? So your energy in can be in any form, just like you can, throw money into something at Walmart. It doesn't matter what you're buying. Money is adding to the value of something, right? And so in this way, heat can provide activation energy, but it's not as controllable or as regulated. So heat will make reactions go faster, and cold would actually make them go slower. But biological systems require a way to regulate reactions, a more regulatory way to control reactions, not just relying on heat. And this is where the enzyme comes in. a bit. So I wanted to just kind of draw an analogy for you here. Imagine if you had a sort of a long, narrow tube, and there was a metal rod that had to be sort of shoved into the tube. Well, if the metal rod had a kink in it, like this, it wouldn't really fit into the tube. So in order to make this fit, you would have to use some energy to bend the rod. You might consider putting the rod in a vise, right? So you go you go to the workshop. You have this large vise. You put the rod in the vise like this, and then you can push and pull on this using your arms or a hammer or some device to bend the rod into a shape that's more conducive to fitting into the hole, right? And then it would easily slide in. So you used energy to change the shape. And of course, shape in molecules is very closely related to how much energy they have, because the positions of electrons and how they are pushing and pulling on each other, according to that Vesper theory, is what determines the shape of a molecule. So how can we bend and what can we use as a vise to put molecules in to get them to be the right shape so that they'll do what they need to do? They'll bond. And that's, of course, when we use what's called the enzyme. So an enzyme is a biological catalyst. That essentially what it does is it lowers the activation energy of a reaction. Allowing it to happen far more frequently or easily. Allowing it to occur, that says occur far more frequently. I'll go back in a second for you. Okay? In other words, an enzyme essentially puts molecules into a specific position, kind of like a vise, and it causes a slight shift or change in what's going on with those the relative positions of those two molecules, and allows for it essentially puts in energy, just like hammering puts energy into the rod to bend it into the right shape. The protein molecule that forms the enzyme, and I should have mentioned that they are proteins, right? Enzymes are proteins. We talked about that before. These protein molecules can essentially put physical pressure on molecules. And the physical pressure is caused by all of the functional groups with all of their polarity pushing and pulling on other molecules. So a few terms. We have words, so we have an enzyme, and then we have a substrate, which is the molecules that the enzyme acts on. Just move that over. There. An enzyme and a substrate. So just about every reaction in biology that we study has an enzyme associated with it, which means there are literally billions of protein enzymes, molecules that can do this. So the enzyme is the protein molecule itself, and the substrate is the molecule or molecules, because sometimes they will allow two things to join or break apart, that it acts on. So these are the two main words that we need to understand. Okay. Now, remember, a protein is difficult to draw, right? It's a spirally chain of amino acids that's kinked and bent on itself like this because of secondary and tertiary structure, right? And it's complex and twisty. And the reason for it is because on each of these little spots, there are functional groups on the amino acids. And in fact, there could be a second spirally protein attached to it, right? The quaternary structure of proteins. So they're very complicated. So to make it simple, we're just going to draw proteins as globby sort of circles like this, because it's too hard to draw all that complexity. But when we draw this circle, you have to imagine it in this way. And all the little functional groups that occur all over here, all over the place, are responsible for pushing and pulling and twisting. But in some cases, they might also be places where other molecules could either be attracted or held in place. So what typically happens is regions on the molecule that have just the right shape, like say for instance this cup-shaped region here, that might be a spot where a molecule could actually sort of hover in place and be attracted there by interactions of functional groups. And it might be held there long enough so that it could be broken down, maybe the enzyme holds it in that position, but when it locks in there, the pushing and pulling of electrons would change its shape ever so slightly, which would mean that it could now be snapped apart and then broken into two. So this could be an enzyme that catabolizes, right, breaks apart something. Or there could be an active site that has, two bumps, where two molecules could go in and be joined together. It all depends. So what we draw is we tend to draw the molecule as a blob, but then we sort of add a spot to it, like a little circle or something, a dent, and we call it the active site, or the activation site. I think the active site is what your textbook uses, so we'll call it that too. Just looking it up. Yeah, they use active site. So the active site is where the substrate would attach. Where the substrate attaches. So the substrate molecule, and of course, they're all very shape specific. So the special shape, and you can imagine how complex the shapes could be with all that twisting and turning structure of the protein. So the shape can be very specific to a very specific kind of molecule. So essentially, when the substrate latches on to this active site, we draw the substrate molecule in there like this. I'll put an S for substrate. Then the enzyme is exerting pressure on this molecule or pair of molecules. And it's just like bending of the bar in a sense. The energy is coming from the pushing and pulling of all the functional groups and the electrons and the polarity and the charges, right? It's all about Vesper theory and electrons pushing and pulling. And that essentially means that whatever reaction is going to happen here, because it's being sort of helped by this extra energy, this input of energy, the activation energy can be much lower, and the energy or the reaction can happen much quicker. Okay? Pictorially speaking, we could have an enzyme that has two bumps on top. And these two bumps are perfect for, say, a glucose molecule to fit in there. So one glucose molecule comes along, and maybe another molecule would be fructose. And the fructose molecule fits in here. And so while they are sort of sitting in that active site, they are now being sort of squished and bent and pulled, and that energy can form a bond between them, and now the enzyme can produce or can cause the reaction of producing sucrose, the disaccharide, more easily. So here's an example of a synthesis reaction or an anabolic reaction where we're building something, but the same could work in reverse, where the enzyme provides the energy to break something down. If we were to just have a glucose floating around free, and a fructose floating around free. First of all, they have to find each other. So they'd have to be mixing and mingling in the soup. And the nice thing about the enzyme is it locates them right close together. So the chances of them bonding are much higher, obviously, right? So the enzyme also serves as a simple way of getting them together, like matchmaker. But it also then, if we didn't have the enzyme, these things might bump together. But it's kind of like putting the bent rod into that tube. They're not quite the right shape. There's too much energy required to get them to bond. In other words, we have to break some of the OH bonds at their functional groups and reattach them, right? We have to get the water that comes out, the water that's released in this kind of reaction. It's a condensation or a dehydration reaction. And so we have to get energy to do that, and maybe just bumping into each other wouldn't cut it. But if we put them in the enzyme can hold them and give them just a little twist. Just a little bit of a physical twist, which creates the conditions necessary for that bond, the OH bonds to break, the water to leave, and the new bond to form. So that's kind of a pictorial sort of picture of it. We often will draw sort of graphical forms for these activation energies, right? Now, there's two things that can happen. So you have we can draw a little graph here. And on this side, we'll be graphing the energy. And over here, we'll be graphing sort of like what happens over time. Whoops, let's go back up there, sorry. What happens over time. So typically, if you have a molecule, it has a certain amount of energy. So we'll start off with, say it's here. It's like you having a certain amount of money, right? Now, if we want to change that, we want to either do two things. We either want to add energy to this molecule and cause something to happen, or we want to take energy away from it and cause something to happen. So the first thing is we have to break the bonds, which means we need to put in a boost of energy, and then the bonds can break. And maybe when they're done, the new molecules are lower. So on this graph, we have the initial energy, and we have the final energy, which is obviously much lower. But we also have this little boost of energy, sort of this part. That's the activation energy that you need. So that would be sort of the way the reaction would be. With the enzyme helping along, though, running out of colors, so I'll pick, let me see if I can find something else here. How about this nice orange color? With the enzyme present, because it's helping the process, maybe the graph actually looks like this. So that the activation energy is much lower and the reaction happens much more feasibly or easily. Now you'll notice in this case, the initial energy, let's put EI, initial, and down here in green we'll put the energy level final. If the final energy is less than the initial energy, then there must have been energy given away in this reaction. Energy is lost, right? Or given off. Where did that go? Well, that energy might be stored in the new bonds of the new molecule, but it might also be, there could be all kinds of things. Typically, we see heat as one of the ways that energy is lost. And when this happens, energy being given away, you always have a lower state of energy after than a higher state. Then what we call that an exergonic reaction or an exothermic reaction. Let me see what your book uses. So we use the same words as your textbook. They use an exergonic reaction. Exergonic reaction. That means that energy is sort of given away. Now that energy will go somewhere else. It doesn't just float off into space. I mean, it could just be heat and that's it. But typically what happens is the energy is now locked up in other products or in other molecules and new bonds that form. Now the other thing that can happen though is sort of the opposite of this. You can have a reaction, if we draw our graph again, And this time, what we'll do is we'll take a reaction that actually needs more energy, and when you're done, the actual products end up with more energy than the reactant. So there will be a graph where you have your initial energy right here, call that EI, and energy will have to be added to the system. So there will be an activation energy, but when you're done, E final will be higher, right? And we still have this little bit of extra energy which is required to activate the activation energy. Now, in order for this to happen, because the energy at the end is greater, you have to put energy in. Energy is not lost. Energy is put in. So this is an endergonic reaction. Endergonic. Go back a bit. Oh, I'm standing in the way, sorry. Okay, so an endergonic reaction. Energy has to go in. With an enzyme, if I go back to my colors here, what the enzyme would do is they would cause the graph to proceed more like this and lower the amount of activation energy. However, you would still need to put energy in to this situation because it's going to end up with a higher amount of energy no matter what, right? So it's a little bit confusing to think about what the activation energy is, which all reactions require. And then this is an energy in endergonic reaction because the products end up with more energy than the initial reactants, right? Whereas in the other case, we still put a little bit of energy in, but we got more energy released than we put in. It's kind of like lighting a match. It's a small amount of energy, but once you start that fire burning, you get tons of energy out, right? So it's kind of the same idea. All right. How did that little line get on there? I just noticed this weird thing. I must have touched that somehow. Okay, so that's kind of how enzymes basically work. There's one more thing we have to talk about, though, because we have a couple of minutes, and that is that enzymes can be actually regulated. So watch this. Let's call this regulating enzymes. This is what makes biology so cool and so complex. Let's take an enzyme and let's put a very specific shape in here for the active site. And so what's supposed to happen is there's a substrate that looks like this, and it's supposed to fit in the active site. Okay? But there's another molecule that's a little bit different, but it has a very similar shape. Okay? This molecule could slide into here and fit in the enzyme. And if this molecule was sort of in high concentrations, this would happen more often. And it would inhibit the substrate. It would get in the way from bonding with the protein, from bonding to the enzyme. If something inhibits something, it stops it from happening. And so this purple molecule, as it builds up in concentration, will start shutting off the chemical pathway that this enzyme is trying to produce. Because that purple thing will keep getting in the way, and effectively this would shut down this stage of whatever reaction was happening. And since biochemical reactions often occur in many, many, many stages, a simple reaction like glycolysis is 50 or 60 different stages of reactions. Sometimes what happens is you don't want too much glucose, so you're making glucose in a plant, say, through photosynthesis. One of the one of the products of one of those reactions, as it builds up, could go back and inhibit the enzyme necessary for stage 1 or 2 and shut everything down. So this is a way of monitoring, right? You want to make something, but if you make too much, you want to shut off the process. And so the product that you're making might actually inhibit some of the enzymes that work in the process. And as they build up, they shut it off. Now, of course, then they would begin to deplete. And as they depleted, there wouldn't be enough of them to inhibit, and then the green substrate could then bond again, and the whole process would. So it's like a regulatory process, okay? This is called a competitive inhibitor. Competitive inhibitor, because it competes for the same site inhibitor. A competitive inhibitor of the enzyme. It's competing for the same spot where the substrate would like to bond. All right, now there's another way that you can inhibit an enzyme. Here's an enzyme that has a little spot on the bottom, and it has an active site here at the top. So this time, our substrate is supposed to bond with that. So there's our substrate that's supposed to fit in the active site. But another molecule comes along, this purple one, and it bonds down here. It finds another place on that enzyme where it's happy to join up. A little spot where the functional groups push and pull and attract it. And of course, when it joins up, the result is that it pushes and pulls and twists the protein, and with it joined, actually what I should have drawn here, I know that you're gonna get mad at me. I'm gonna take this here and just put it coming in, so it hasn't joined yet, right? It's gonna join up there. When it does join though, it changes the shape of this molecule, which causes it to do this. And now you can see what's happened. The active site no longer fits the substrate, and it will not be able to bond. This is like a shape-shifting inhibitor. It's called an allosteric inhibitor. This is an allosteric site at the bottom. So an allosteric regulation. Oh, no, I'm spelling. Let me write that properly. Allosteric. I'm going to write that in purple because it's the purple thing. 2 L's. Allosteric. Allosteric inhibitor. But this is weird because maybe it doesn't inhibit, maybe it helps. By the same token, that addition of that little purple molecule might actually create the active site that we need. So another way that an allosteric site can function, I know you're catching up with me, so I'll try to keep that up there. Another option for the allosteric inhibitor is that the protein begins with the wrong shape at the active site. The allosteric molecule comes into play and results in shifting the protein into the correct shape, like this. I'm going to color in this guy up here too because he looks right. And now the correct shape is open, and now the other molecule can easily bond. So this is also an allosteric regulator, but this would be an allosteric sort of enabler, right? So typically, because it works both ways, it can inhibitor, and this one would be sort of a enabler. I'm not sure if there's an actual name for that, enabler. We basically refer to both of these simply as allosteric regulation. Allosteric means shape-shifting, allosteric regulation. But there's 2 ways it can happen. In the first case, the molecule can turn off the protein enzyme by changing its shape to the wrong shape and shut it down and inhibit its purpose. Or it can actually turn it on by bumping into it and causing it to change into the proper shape. So it can either make a reaction happen or it can stop a reaction. Right? Whereas the other one, the competitive inhibitor, because it's jumping into the same spot, it pretty much only stops the reaction. It doesn't do any enabling. Okay, and that's all we need to worry about for enzymes for now. So we'll call that a day.